Okay, now in this particular discussion, we'll be talking about some of the common applications of a long short-term memory network, or LSTM, right? We have seen the basic idea of an LSTM. Okay, and in this study or in this discussion, we'll be looking at how you can use LSTM to solve different problems, right? We'll start with some examples from textual data, and we'll be, you can say, later on, seeing, looking at if we can apply LSTM to maybe an image as well, right? So this first slide is actually just a recap of what we discussed a little while back, right? An important point here is that when you are implementing an LSTM, right? And for implementing an LSTM, you just write model.add LSTM and you write say 2 here. Okay, so some of the students think that this 2 means I have 2 cells like this. Okay, means you have an input coming here. This is one cell, this is second cell, which is not true. Okay, because on this axis, you actually have time. You have as many cells as the length of the sequence. When you write LSTM2, it means in the hidden layer, you have 2 neurons. Okay, which is shown in this illustration by this, you can say this red, you can say circles. Okay, and similarly, this is the size of your input. So whenever we implement an LSTM and we give a number, so that number is actually number of neurons in the hidden layer. Please do not think it is the number of boxes, right? Within one box, how many hidden neurons you have. How many boxes you will have, it depends on the length of your sequence, right? This is very, very important because many I have come across many situations where uh, I came across this confusion among the students, right? Okay, so now let's start a discussion with LSTM for sequence classification. And we start our discussion with many to one mapping. Many to one means input is a sequence and output is, you can say, a single value. And if you remember, we have done this example when we were studying basic RNN. And the example we did was sentiment classification, where input is a sequence and output is a single number, which is positive or negative, or the rating of that report, right? So if you remember, this is something we already did, that if you want to solve this problem with a simple RNN, okay, so first you create a model, you have an embedding layer, and then you have multiple layers of simple RNN. Simple RNN means no LSTM, just NH. And finally, this is your output layer. One neuron. Why one neuron? Because sigmoid activation function, because we only have 2 classes, whether the review is positive or negative, right? Now, if you want to solve this problem with an LSTM, all you need to do is that instead of the simple RNN, you replace it by LSTM. So you see, from the viewpoint of implementation, it is so simple. You don't need to worry about all those numbers, how many parameters, and you, from the viewpoint of implementation, you just write LSTM and any number. For example, this 32 here means 32 neurons in the hidden layer, and rest everything is handled by the program itself, right? So you see, exactly same code. Instead of layer simple RNN, we have the layer LSTM. Okay, and you can solve the sentiment classification problem. You can compare the performance of a simple RNN or an LSTM, right? And if you want maybe GRU, you can simply write GRU here. So it will be with GRU. Okay, so you see it's fairly simple. Now let's see, what if we apply, or we try to apply LSTM on images, right? Which does not look very intuitive if you see it for the first time, because we have been saying that LSTM is for sequential data, right? But we can play smart and we can convert an image into a sequence. Okay, now let's see how do we do that. From day one, we have been talking about this MNIST dataset. Okay, digits 28 by 28. Okay, so you see, I can look at this image row by row. Okay, so I say, okay, this is my first row, second row, third row, and every row has 28 values. Why? Because there are 28 columns. Okay, so now you see, if I look at this image row wise, so it is actually a sequence of length 28. Okay, which we are playing smart and we are trying to interpret it in that way. So what I do is I make an LSTM. I feed the first row here, then the second row, then the third row, and then the last row. Just like we feed a sequence of 28 words. And then since there are 10 classes, so I have a softmax layer with 10 neurons. Once I have seen the complete input, and it can actually perform classification. So you see, although our data was not sequential, we can still implement an LSTM which is doing classification on images by treating our image as a sequence. You can treat it as a sequence of rows. You can treat it as a sequence of columns, right? So if I show you the implementation, it's fairly simple. You see, you create a model, you have an LSTM layer with 128 simple neuron. This is important that you are telling your program, your LSTM, that how many timestamps are there? 28. Why 28? Because there are 28 rows. So this is 28 timestamps. How many values are there in each timestamp? Means in each row, how many values are there? Since it was a square image, so that is also 28. Okay, so you just need to tell how many timestamps are there and what is the size of vector in each timestamp. Okay, so I have only one LSTM layer, nothing else, nothing fancy, and then a fully connected layer with software activation function. So you see, only with one layer, it is giving you very high accuracy on test data, which is like 98%. Okay, only with one layer of LSTM and raw pixel value. So it means if I can manipulate with more layers, and maybe I can get something very close to 100%. Okay, now why I should feed it one row? Okay, what if I feed it two rows at a time? Okay, it will still be a sequence that I feed it two rows, then two rows, and then two rows. Okay, so it means in total, how many rows would be there? 14. Okay, but when I feed it two rows, how many values do I have in one, you can say, sequence? I have 56 values. Why 56? Because 28 plus 28. Okay, so you see, you can reshape your data in such a way, 60,000 images. Okay, how many timestamp? 14. 14 timestamp, and how many values in one timestamp? 56 values. Because when you take two rows, total number of values is 28 plus 28, which is 56. Or you can also go for columns or anything, right? So this is just to tell you that not necessarily you always pick one row. You can pick two rows or three rows or four rows or maybe columns. It depends on what you are trying to implement, right? And previous LSTM which I showed you had one layer. Okay, we can make a very sophisticated sort of model where you have one layer, second layer, and then you have more than one fully connected layer. In between, you are adding dropout because you are making a deeper network, so there are chances of overfitting. So we are adding dropout. So you see, you can make a very fancy, deep model with LSTM which can solve image classification problem. Now, another improvement could be that when we are making this LSTM, we are feeding image directly to the LSTM. And we know that whenever we are dealing with images, if we first perform convolution, then it gives us something better than raw pixel values, right? So there's a combination which is very, very common, which is called CRNN. This C is for convolutional network, and RNN could be a simple RNN, it could be a LSTM, it could be a GRU, any recurrent neural network, right? But normally we use the term RNN. It does not mean it has to be basic RNN. It can also be any type of RNN, LSTM, GRU, or any other variant, right? So what we do is we feed our image to a CNN. Okay, it means pixel values are converted to features. Then those features, we treat them as a sequence. And we feed that sequence to an LSTM. So you see, it seems like a very, very powerful combination where you are combining the powers of a CNN and RNN, and it is called CRNN. Okay, maybe next week or the next to next week, we'll study something which is called RCNN. Okay, please do not confuse the two. What is it? I will tell you later when we study this topic. But there is something which is called CRNN, which is convolutional recurrent neural network. Means you have convolution as well as recurrent. But I'm just telling you that after 2 weeks, or maybe in the next week, we'll be studying something which is called RCNN. Okay, it is something different. What is it? I don't want to discuss now, but just be careful that these are two very similar terminologies. So be careful. Okay. Now, let's get back to CRN. Okay. Now, maybe we do this example, then we can do a break. So we go back to our CFAR data set, which has 10 classes. It is a colored data set, right? 32 by 32 images. Okay. And we want to do image classification, but we want to do it with the CRNN, means convolution as well as recurrent neural network. Okay. We load our data, which we already know. Now, this is the important part. Okay. We perform convolution. Con2D is the name of the layer. Okay. 50 filters. Filter size is 3 by 3 with padding and stride of 1 by 1. Okay. So it means that my images were 32 cross 32 cross 3. Okay. When you apply 50 filters with padding, the output would be 32 cross 32 cross 50. Okay. A recap of CNN. Okay. That the output depth of output volume is same as number of filters. Then we apply pooling with 2 by 2. Whenever you do pooling with 2 by 2, spatial dimensions are reduced by half. So it means we get a volume of 16 cross 16 cross 50. Okay, this is a volume, this is a feature map. Now we want to feed this volume to an LSTM. Okay, but you see it is 3-dimensional. We need to convert it into 2 dimensions so that we say, okay, these are the timestamps and these are the number of features. So what we do is we reshape it into 16 cross 16, which is I think 256. We reshape it into 256 cross 50. So now see what is happening. I have 50 values in this column, then 50 values, then 50 values, and this is actually 256. So we have 256 timestamp. Okay, and in each timestamp we have 50 values. So now we have converted our 3D volume into a form which can be treated as a sequence. Now, since it is just like we were doing with MNIST dataset, now we can have an LSTM layer or more than one LSTM layer, and we can also have a dense layer Y10 because we have 10 classes. So we have 10 neurons, and finally we have the activation layer, okay, which is softmax. So just like any other model, you train it with cross entropy loss using model.fit, and you can evaluate it on the test data and print the accuracy, right? So you see, this is something very effective where you are combining the powers of two very, you can say, effective techniques. CNN, which is converting your pixel values into effective feature maps. And before you can feed it to LSTM, you just reshape it, right? So we were doing pooling, so we had a volume of 16 cross 16 cross 50, which was in 3D. So I converted it, reshaped it into 256, 50. So it will treat it as 256 timestamp and 50 values at each timestamp, just like it was doing previously, where you had 28 values and there were 28 timestamps, right? So if you are trying to solve a classification problem, maybe if it is simple, only CNN will do. But it's a good idea that you can also try combining CNN with an RNN just to see that what it gives, right? So maybe here we can take a break, right? And we continue our discussion after the break, right? After the praise, and then we will restart, okay? Okay, so welcome back, and now we'll be continuing our discussion. So what we'll be doing is we'll be doing a few more example of LSTM, few applications, but now we'll be dealing with sequence to sequence mapping problems, right? Okay, so when we say sequence to sequence mapping, there are different case studies that we can see. For example, we can talk about machine translation, where you have a text in one language and you can translate it into another language. Then you have the case of speech recognition, where you have a signal, which is a sequence, and you have to produce the transcription of what the person is saying. And then you have another example where you have text or handwriting recognition, where something is written by someone and you have to convert it into the transcription using handwriting recognition, right? So these are few examples of sequence to sequence mapping, right? So we'll do some, you can say, detailed study of machine translation, So you see, prior to deep learning, this translation from one language to another language was considered very challenging task, right? But today, if you have sufficient training data available, maybe with less than 100 lines of code, you can write a program which can translate from any language into any other language, right? Less than 100 lines of code, but the only condition is that you need to have sufficient training data, means pairs of sentences in one language and in the target language, and then the job would be done, right? So the general architecture, this is the general architecture. Of course, the low level details can vary, is that basically for such a system, you have two parts. Okay, one part is called the encoder, and the other part is called the decoder. And both of these are actually LSTMs or GRU or RNN, means any type of RNN, right? So this is your input, means you feed it word by word to the encoder, and then the encoder will produce an encoded representation of this, you can say, sentence. Then you have a decoder part, which will produce your, you can say, the same sentence in the target language, right? So, for example, if we have a sentence in French and the English translation, right? So, by the way, this is an example from a tutorial, right? So you can also find it on the YouTube. So you can have different number of words. For example, in the French version, I have 5 words, right? And in the English translation, I will have 6 words, right? So the length of these can vary, which is common. So the encoder would be any variant of LSTM where we are feeding one by one, okay? And then this will produce an output, which is the, you can say, encoded representation of this complete sentence. And then you will have the decoder. Okay, this blue part, this is the decoder part, which will take this encoded representation and produce the output, right? So what it will do is it will produce the first word, and then you produce the first word as an input, so it produces the second word. Then it goes back as an input, so it produces the third word, and so on, right? And how do you train such a system? For example, if we want to make a translator from French to English or vice versa, we need pairs of sentences, right? So one sentence in French and the corresponding translation in English, right? Similarly, this is your one training example. So you will have many such pairs, okay? English, French, or French, English, or whatever languages you are targeting. And this is the way you will train such a system. And you can exploit the same idea, not only to train a translation system, but also to make a chatbot, right? So you see, instead of translation pair, the only thing you need to change is the data. That now your data would be a question and the corresponding answer. Okay, so you will have pairs of question answer. You will have a huge number of such pairs, and you can feed them to a very similar architecture which you are using to solve the language translation problem. So when you will feed it with a question, it will generate the corresponding response, right? So this is, I think you must have observed that today almost all the vendors have automatic chatbots, right? If you have to register some complaints or you have some queries, then rather than a human answering you, the first step is that you will be dealing with a chatbot, right? Which is trained in something like the way we are discussing here. Okay, another important problem that we can solve with this architecture or the similar architecture is that, which is called image captioning, right? We discussed it somewhere in the middle of our semester, but we did not see in detail how to actually solve it. We just said that this can be solved, okay? So you see, for example, if this is the image, we want this maybe as a caption of this image. For example, a cat sitting on a chair, right? Of course, this is not unique. There can be multiple captions, but this is one possible caption, which is actually a sequence of words. Okay, so, and the length of the sequence can vary. So what we can do is, you see, we have already been feeding images to CNN. Okay, for example, if I feed this image to this architecture looks like AlexNet, right? So if I feed it to AlexNet, maybe there is convolution pooling, and then we have fully connected layer 4096, 4096, and eventually we have a softmax layer with 1000 neurons because we are solving a 1000 class problem. So what we can do is that we know that this part, this is a compact representation of this image, right? Means whatever I am feeding to this, eventually I get a vector of 4096, which is encapsulating the complete information of this image. So what I can do is I can actually drop the softmax part and I can connect this fully connected layer with an LSTM, okay, which is producing a sequence of words. So now what will happen is I will train this model. How will I train it? Input would be image and the output would be the caption. This is my training data, right? So this is one training example. Similarly, I will have another image, another caption, another image, another caption. I will have thousands or millions of such examples. And once the model is trained, I feed it with a new image. So the convolutional part will actually learn or find out what actually is represented in this image. And the LSTM part, similar to the translation part, this will generate a sentence, okay, one word at a time. So you see, we know all of these modules, and using these Lego blocks, you can put them together and come up with very interesting solution, right? There's no new concept. We already know all of these. We just have to plug them in the right combination to solve such problem, right? But anyways, let's come back to the translation problem, which we'll see in a little bit detail, that we are feeding it with an English sentence and it is generating the French translation or vice versa, right? So let's see how it will work, right? So the first thing we should discuss is that you see, against any sentence in a language, there can be multiple possible translations, right? And some of these, maybe grammatically, all of these are correct, but maybe we try to pick the one that makes more sense or that is more pleasing, right? Means, for example, for a French sentence, we can have three different translations. Maybe is visiting, is going to visiting, or maybe we change the order. So you see, okay, normally in daily language, which of these will be using, right? So maybe that is more preferred, although grammatically all of these could be correct, right? Now, what we do is that you see when we are solving this problem. So here you have a softmax layer, which is giving you probability of every word. Okay, so you are actually picking that what should be the first word, what should be the second word, third word, fourth word, and so on. So normally, what we do is we use a greedy search that at every time stem, we pick the word for which we get the maximum probability, which makes sense, right? So basically, what we are trying to say is that this is your encoder part. When you are doing the translation, here, suppose you have 10,000 words. So you have 10,000 probabilities. And you say, okay, this word has the maximum probability, I'll pick this. Okay. Similarly, for the second word, you have a softmax layer, you have 10,000 different possibilities. You pick the word which has maximum probability. Okay, so it makes sense that when we are making prediction, we pick the most likely word. Okay, so for example, at the first time step, the most likely word was this. Then at the T2, the most likely word was this, and so on, right? This is okay, this is fine, but sometimes it can lead to results which we do not prefer, right? For example, grammatically, maybe this is correct, Jane is going, right? Because going is something which occurs frequently, so naturally we expect that the probability of going would be higher. So this is grammatically correct, right? Jane is going, or but maybe we want Jane is visiting, but since going may have higher probability, so your model will output going, right? Jane is going to visit rather than saying Jane is visiting. Both actually mean the same thing, but maybe this is what we prefer. So that's why sometimes we say that greedy search is not something that we desire. So what we do is we do something else which is called beam search. Okay, I'll explain in detail what is beam search. So for beam search, first we choose a parameter which is called beam width. Okay, so in this case we have chosen beam width to be 3. Okay, now what does this 3 mean? It means that at every time step, instead of keeping the word which has the highest probability, we will keep 3 words with highest probabilities. Means maybe this has the highest probability, number 1, rank 1, and maybe then this is rank 2 and rank 3. Okay, maybe this was a 0.1, 0.05, 0.04, and rest of the words, 9,000 something, they have lesser probabilities, right? So it means rather than just keeping the maximum probability, the word corresponding to maximum probability, we keep top 3 words with maximum probabilities, right? So we are keeping these 3 words. Now, what will happen? This was T1. Okay, this was for the first word. When we have to make decision for the second word, right? So what we do is we say, okay, let's fix the first word to be Jane. Okay, we fix this first word and we say, okay, if this is the first word, what are the three most likely choices for the second word? Okay, means I have fixed this first word, which is Jane, and I say, okay, out of 10,000, if the first word is fixed to Jane, what is most likely second word? Maybe is. What is another choice? Means second most likely word, maybe visited and visit. So this will give me, you can say, three combinations. Similarly, I repeat it for the second word in. That okay, if I fix the first word to be in, what are the three most likely choices for the second word? So maybe out of 10,000, I have Africa, visit, September. So I get these three. Okay. And similarly, I do it for the by fixing the first word to be September. And then I say, okay, if the first word is fixed to September, what are the three choices for the second word? Now, in total, it will give me 9 combinations, right? So you have 9 combinations here. Out of these 9, what you will do? You will, since the beam width was 3, again, you will pick the 3 combinations which have highest probabilities, right? Because each of these will have a probability. So you say, okay, I pick 3 words, means you will again come to 3. And then you will repeat this process for the third word. That, okay, if the first 2 words are these, what are the 3 choices for the third word? If the first 2 words are these, what are the 3 choices for the third word, and so on. So you will again end up with 9, and out of those 9, you will again throw away 6 and keep these those 3 which have the highest probability, right? So you see, this way, every time, depending on your beam width, you are actually making multiple choices so that you end up with maybe a better solution, right? So what we did, we first define a beam width, which was 3 in this example, right? And then what we do is that for each of the 3 words, we consider what is the most likely next word, right? It means I will fix this word and then say, okay, out of these 10,000, what are the 3 most likely words? If I fix this, what are the 3 most likely words, and so on, right? So once we are done, we'll have 9, you can say, possible choices. Out of those, I'll pick the 3 most. Okay, so maybe I'm left with these 3. Now I have to repeat the same process, that I fix the first 2 words, that okay, first word is in, second is this, what are the 3 choices for the third word? Okay, so similarly, I fix the first 2 words to be these, and I repeat this. So you keep on doing, and eventually you will have a, you can say, we expect to have a better translation as compared to the greedy search. Now, if you want to see how we are computing probabilities, there's a simple way, right? I'm showing you by this illustration, where on this axis we have time. Okay, it means we are predicting 4 words. We are predicting a sentence with 4 words. Okay, and at every time we have probabilities that, for example, for the first word, which is this first row, what is the probability that it was the zero point 0.4, cat 0, is zero point 0.3, red 0, and so on. There are many words, but we have just listed, you can say, few of the words. Okay, we say in this example, beam width is 2. Okay, so beam width is 2. So at T0, I pick 2 words which have highest probabilities. So these are 0.4, which is the, and zero point 0.3 is. Rest is either 0 or very low. So I have picked these 2 words. Why 2 words? Because beam width was 2. Okay, so the word da has probability 0.4, is has probability 0.3. Now, what should be the next step? The next step should be that I will fix the first word to be the. Okay, and I say, okay, if the first word is fixed to the, what are the most likely 2 choices for the next word? Okay, and how will I compute the probability of the sequence? For example, if it is word the probability is simply the product of 0.4 and 0.1. Okay, so now you see, if I fix the first word to be the most likely choices are second word is also the, or the second word is cat. Okay, because rest are very low values. What is the probability of sequence? The zero point 0.4 into 0.1, which is 0.04. What is the probability of the sequence? The cat, 0.4 into 0.2, which is 0.08. Now we have to repeat the same process by fixing the first word to be is. If the first word is, again, the two most likely choices are for the next the and cat. So what is the probability of is? The zero point 0.3 into 0.1, which is 0.03, 0.3 into 0.2, which is 0.06. Okay, so now I have four combinations. Out of this, what I need to do, I need to keep only two combinations with maximum probabilities and throw away the rest. You see, in the previous example, the beam width was 3. So we were getting 9. Out of those 9, we were always keeping 3. Here the beam width is 2. So every time I'll be getting 4 combinations. Out of 4, I'll pick 2 and I will throw away the rest 2. Okay, so we pick the cat, we pick is cat, and we throw away these 2. Okay, so it means we have one sequence is this, one sequence is this. Now what we do? Now we fix the cat as the first and the second word, and we search for the third word. Okay, that if the first word is the, second word is cat, what are the most likely choices for the third word? Okay, so maybe they are is and red. Okay, now what is the probability of this sequence? The cat is zero point 0.4 into 0.2 into 0.8, okay, which is 0.064. Similarly, the cat red is, you can multiply them together, and same process you repeat for the sequence is cat. You have these two choices and so on. Okay, so you will keep on doing this, and eventually you are left with two choices. Okay, when you reach the final timestamp, out of those two choices, you will pick the choice which has more probability. So that would be your final output, right? And sometimes when you are computing it, maybe for understanding purposes, maybe it is easier if you represent it in the form of a tree. Okay, it is only for if you are computing by hand. Otherwise, this will be done automatically by the machine. So if you want to do it by hand, you see, you make a tree where at t0 you have all the choices and all the probabilities. You keep the maximum 2 and you ignore the rest. So if you fix the, again, you have all of these choices, all the possible words. If you fix is, you have all the possible words. Okay, and for the probability of each sequence, you simply have to multiply them. For example, zero point 0.4 into 0.1 is 0.04, zero point 0.4 into 0.2 is 0.08, which is the probability of the cat. Similarly, you can do for rest, and again, you keep only two maximum and you ignore the rest, right? So if you are trying to solve it by hand, it is relatively easy if you do it in the form of a tree. Okay, now coming back to some high level abstract discussion, that suppose we have that model. So this is how your training data would look like, right? Sample 1, sample 2, sample 3 means a sentence in English and a sentence in French or whatever is your target language, right? So you will convert that data into numbers using any mechanism, one hot encoding, or simply by counting the frequency. And then you can do padding, and eventually you can represent them by an embedding vector, word to vector, or you can learn embedding. And this is the general architecture of all such systems that you feed your input. This is actually an LSTM. This is also an LSTM. The left part is the encoder part, and the right part is the decoder part. So if you look for the implementation of language translation, right? You can, as I told you earlier, you can easily find very 50, 80 lines of code which would be doing this. Okay, and you can run them, you can train them on some data, and you can actually see the output for yourself, right? You can convince yourself that this actually works, right? So many of the implementations that found, they were like English, French, English, Spanish, right? So just for curiosity, uh, I got some time to implement it. So I thought, okay, let's try and make a translator from English to Urdu, right? So I just collected some data with some small sentences in English and the corresponding translation in Urdu. Of course, the data was very less. It did not converge, but still it gave something which is not very bad, right? So they are very small sentences. Okay, for example, you see, I need help, so it is giving correct translation. I trust you, because in the training we had very small sentences. But of course, since the training data was not too much, so you see there are some silly translations. I'm at home, so it is saying something, maybe I'm sleepy, or something like that. Okay, so otherwise it seems like it is 60-65% okay, right? It is not that bad considering that the training data was not too much. So You see, you can actually make a system like this, just collect some data, and you can have your own translator, which is translating from any language to any language, right? The only thing you need is data. Code you will easily find on the internet, and you can also write yourself. Okay. Now, extending the same idea, okay, which we use for translation, we can use it to generate text. Okay, what do I mean by generating text? That you have a model which is producing text, means you give it some starting words, a sequence of words, and then it will generate a complete article for you, or it will generate a complete book for you, or maybe your assignment for you. Okay, maybe you don't have time for an assignment, so you collect assignments of all your colleagues, you train a model, and then it will create an assignment for you. Okay, it will be nonsense, right? But if your instructor is not reading, he or she is just visually looking at, so there's a high probability that your assignment will get through. Okay, of course I'm not suggesting it to you, right? But this is what some people do to actually test the validity of conferences, right? They use a computer program to produce a research article. Okay, and if they doubt a conference, because there are certain conferences which are meant for money making, so if you submit something, they just accept everything and they ask you for a handsome registration fee. So some of the people who want to test uh, maybe the validity of a conference, they just write a computer program and they submit a nonsense article which visually looks correct, but if you read it, it does not make any sense, right? But visually it looks like a professionally written article. So if a conference is not doing any review, it is accepting anything, then of course that paper will get through. Okay, and same goes for assignment or thesis, that if you doubt a system, you want to test it, you just submit a computer generated submission and see whether the system works or not, right? Okay, now how to actually do that? Okay, so this is the example I have been giving you many times, but I never explained how actually this works. So today is the time we actually see it. That, okay, suppose I give you a sequence of words and I ask you what is the next word here. Okay, you say, okay, the man is walking down. So based on your experience, maybe you are able to guess that the sentence would be something like the man is walking down the street, down the road, or something like that. Okay, because we have seen it many times in the books or literature. We can actually see, okay, this sequence is suggesting that, okay, this should be the next word, right? Now you see, assuming that we have a model which is already trained. Okay, how is it trained? Let's forget it for the time. Suppose we have a model that if we give it 4 words, it can predict the next word. Okay, our model works, it takes 4 words and it predicts the fifth word. So I feed it with 4 words, the man is walking. It will predict the word down. Okay, assuming that the model is trained correctly. Now what I will do is, I will delete or drop this first word and I will make this down part of my input. Now I will feed these 4 words to a model. Man is walking down. So it will predict the next word, which is the. Again, I will drop this word and I will make the a part of my input. Now the input is walking down the, and it will predict the next word. So you see, I can keep on repeating this process as many times as the length of the sequence that I desire. Okay. For example, you want a paragraph of 100 words, so you can repeat this process 100 times. Okay. Now, how this model is trained? You can train it at word level. Okay. How will you train it? It's very simple. You take any novel from the internet. Most of the novels are available in text form, right? You say, okay, I feed it 5 words. Okay, you have a novel which is written like this. So you pick this fourth word as input, and this is your target. Then you pick these 4 words as input, and this is your target. So you see, you from a complete corpus of text, you can take a window. The first 4 words in the window are input, and the fifth is your label. Then you move that window one position to the right, and this is another training example. So you do it on the complete text, and you will have millions of training examples. And once that model is trained, you feed it with 4 words, it will predict the fifth word. You can do it at word level. You can also do it at character level. Okay, that you can actually say, okay, if I give you a sequence of 10 characters, what is the 11th character? Of course, at the character level, it is more difficult to train because words are meaningful and every combination of characters is not meaningful. But still, I have an example which you have the link where this complete code is available. Okay, so I'll not be discussing the code. This is there only if someone is interested in reproducing. Otherwise, you can just ignore it. Okay, so what we are doing is that we are trying to make a model which can generate text for us. Okay, and we are using a character level model. So how it works, I tell you in a while, but let me tell you what is the source. All of you must have read this novel, Alice in Wonderland, right? So this complete novel is available in text form. You can just Google it and you can download it, right? So we have this file Wonderland, which is actually Alice in Wonderland, the complete novel. We load it, right? And we convert all the text to lowercase. Okay, so it means this variable is a string which is containing the complete novel Alice in Wonderland in lowercase. Okay, now what we do? Now you see, uh, we have to train a character model. So I explain maybe with the text which is written on your slides. Okay, suppose I ask you, okay, you have to predict uh, maybe the fifth character or the sixth character given a sequence of four characters. Okay, so or given a sequence of five characters. So how can I make my training data? So I say, okay, if this is my text, this is first character, second, third, fourth, fifth. Okay, so B O O K space. These are five characters. This is my input. So input is B O O K and space. And the next character I, it is my output. Okay, so this is one training example. Then I move this window one position to the right. So now my next training example is O O K space and I. This is my input. And what is my output? My output is N. This is my Y. This is my second training example. So you see, you keep on moving your window. So now this is your input and this R is your output. So you can guess that this will produce millions of training examples, right? There's a small code which is doing it, but you can just I'm not explaining it. You can ignore it, right? So the example you see at the bottom is explaining the same idea which I just discussed. That you have this five character CHAPT, okay, and the next character is E. Similarly, when you have HAPTE, the next character is R, and so on. Okay, so you can guess that this will produce many training examples. And you have input, you have target. Now you can actually train the model, right? So maybe model will make sense. So maybe I can spend time explaining this. This is a sequential model, LSTM layer, right? And eventually you have a dense layer because you are doing classification that what is the next character, okay, and how many characters are there. In this particular example, there were, I think, 47 characters, including all the punctuation marks, letters, and you can say A to Z, which are 26, and so on. Okay, so it depends how many characters are there. Now, once the model is trained, you see there is no test data. Okay, so all you need to do is, this is your trained model. You will feed it five characters and it will output one character, say X. Then you will make this X a part of input, again feed five character including X, and it will predict the next character, say Y or whatever it is. So you can repeat this process as many times as you like. For example, in this case, I think they are doing it for 1,000 times, right? So anyways, let's see what we are doing here. So this is an example of a text from the original novel, right? Means this is the type of text which was used to train this system. And this is our seed text. Seed text means if we give this sequence of characters, I think these are 100 characters. Okay, you can check from the code. It will predict the next character what is coming here. Okay, and then, for example, you see when we give it this sequence of characters, and it is predicting a space. Okay, afterwards, and then we make this space a part of input. We feed the next character till here. It will predict E, and so on. Okay, so you will repeat this process 1,000 times. So it will generate a sequence of 1,000 characters. So this is the output the model has generated. What can we see from this output? Many of the words are, you can say, meaningless. They don't make any sense. But if you visually look at it, your model has learned that it has to group characters. Okay, it does not know that they are words. It just knows that it has to make groups of characters which are separated by a space. It also knows that approximately after 80, 85 characters, there's a new line character. So it goes to the new line. Okay, it has learned the formatting. Some of the words are meaningful, some of the words are not meaningful. Visually, it looks like something, but it does not make any sense. Okay, neither grammatically nor you can say from the viewpoint of orthograph, because there are many spelling mistakes. Now let's say we train this model a little longer. Okay, these are all the observations which I have discussed. So now you see, when we train it for you can say a relatively larger number of epochs, now in this text, many words, almost except few words, most of the words are actually valid. Okay, means you see, herself, flying, all of these are actually words which exist in the dictionary. Of course, same word is repeated. For example, this word little is repeated a lot of times, but still it seems much better than what we had previously. Uh, but again, if you read it as a whole, it will not make any sense. Okay, but if you submit it somewhere and they are not reading, they're just visually looking, okay, it looks fine, then it might get through. Okay, so as I told you, that this is something very very interesting. Okay, so what you can do is, you can take, for example, the LaTeX code of many books, maybe many books on calculus, or maybe even deep learning books. Okay, and you can train a model on the source of this book or any other book, and it will actually create an article which will, or a complete chapter. If you visually look at it, if the system is well trained, it will look like a legitimate book. It will have equations, it will have images, it will have tables and everything. Okay, because it would have learned that formatting. Similarly, you can train, maybe you can download thousands of research articles in PDF format, and you can train a model, and that model can generate a research article for you. Okay, similarly, if you have just for the sake of discussion, okay, I'm not suggesting you to do it. You can maybe download, or you can get hold of all the assignments of a course of maybe all the batches. Okay, maybe your assignment number one, and then you can write a program which takes all those assignments as input and generate an assignment for you. Okay, of course it will be meaningless, but visually it will look like maybe a legitimate document, right? And one final comment that which I try to which I discuss in almost every batch, right? I try to give it as a project, but unfortunately I could not find a student who was brave enough to attempt it, right? That you see, we have access to all the poetry in English, in Urdu as well, in textual form, right? So what you can do is you can create a digital poet, okay, which takes all the poetry that is available on the internet. It trains a generative model, and then you give it seed words, right? For example, you give it a word, say maybe Mosam or weather, and it will generate a poem starting with this word. So you see, it is something very interesting. Maybe it is not something which has many applications, but just for the sake of fun or just for learning purposes, you can actually create a digital poet in any language which is trained on the poetry of one poet or multiple poets. And if you train it on multiple poets, then this digital poet will have a flavor of all those, you can say, writers or poets, and it will be something new, right? So you see, this is an interesting idea. So if any of you get some free time and they have some good programming skills, it's interesting to actually attempt it, right? Okay, a short break of a couple of minutes, and then I resume, right? I need to have Okay, now we move to the last topic for today. Okay, and then we'll conclude. And with that, we'll also conclude LSTM applications, right? So this is the last thing that we have to discuss in this topic, which is again, we are modeling, we are doing sequence modeling, but we introduce a new concept which is called CTC. CTC stand for connectionist temporal classification, as I'll tell you in subsequently, right? So why do we need it in what situations? You see, when we are doing language translation, you have a sequence of word in English, you have a sequence of words in French as an output. Okay, it's simple. But in some cases, this sequence to sequence modeling is not very straightforward. For example, let's take the case of speech recognition. Okay, so you see, this is your speech signal, and this is the output. If I ask you which part of this signal is J, which part of this signal is the sound P, you cannot tell. Okay, maybe you can tell, okay, there's a pause here, so maybe this is the word jump, this is over, this is dog, because you see pauses between words. But if I ask you, okay, which part is actually this sound of T, you can't tell it. Okay, so you see, it is a sequence to sequence problem. But when we have to design a system, how do we label data? Okay, one option could be that you can say, okay, you can make windows here, and you can assume that, okay, 3 windows correspond to one character, or maybe 5 windows correspond to one character. But the problem is that everyone talks differently. Okay, so someone is spending more time on J or this word jump, someone is taking more time on another word. Okay, so that's why you cannot decide that, okay, all of these windows correspond to J and then P and then T and so on, right? And even if we assume that we can do it, then you see, how will you label it? Even to label one sentence or one signal, it will take a lot of time. Okay, because you will make windows, and then you will label, okay, this is J, this is J, this is J. So it will take months, rather years, to label even a small data set. So the same problem we have in handwriting recognition, right? That you see, this is a handwritten word TO2. Okay, if I make windows, so maybe I say, okay, this part is corresponding to T, this is also T. Okay, and then I have this all is O. Maybe I make windows and I say, okay, all of these are actually O's, all of these are sorry, T's. And when my model is trained, so if I give this as an input, I will get this as an output. So I say, okay, whatever is repeating, I can delete it, so I maybe end up with 2. But again, this can fail even if you do it, although labeling it like this is very difficult, it is not practical. But even somehow, if you can do it, and suppose someone is writing the word TOO, so what will happen? You will have T labeling T, 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 O. When you decode it, you get T. You don't know that O was repeated 2 times. Okay, so you see that these are only few of the problems that we sorry, encounter in such situations, right? So in order to solve all of these problems, we have something which is called CTC, or Connectionist Temporal Classification, which is suitable for applications like speech recognition or handwriting recognition, where you don't need to worry about the alignment issue, that which part of input corresponds to which label. You just have an input, like image of a handwriting, and you have transcription too. And okay, this is the label, this is the image. You don't worry that where is T, where is O, where is the other O. Okay, and this CTC layer takes care of this on its own. This is a very you can say this was a very big milestone in solving handwriting recognition problem a few years back. That you see, we already have discussed the combination of CNN and RNN, which works for traditional image classification, where you just have one label, it's a cat or it's something, right? But when you are doing handwriting recognition or speech recognition, so maybe you can have a CNN, which is extracting features. You have an RNN, which is giving you a sequence as an output. And then at the end, you have this new component, which is called CTC, which is doing that alignment. Okay. Now, as I told you, this is the state of the art method for OCR or handwriting recognition today, where you will be using this part, which you already know, and then you have one additional decoding part, which will convert the raw output of this LSTM, okay, into this transcription apple. Okay, that this was the input and this is the output. So maybe here you have some raw output, which I will tell you in the next slide, and this CTC decoding will convert that raw output into the transcription. Okay. In order to understand this, we whenever we are solving a text problem, we have a vocabulary. Okay, so in this case, we say our vocabulary is A, E, L, P, Z. So in addition to all of these characters, in the vocabulary, we introduce a special character, which is represented by this hyphen here or dash here, right? You can represent it by any symbol like lambda or eta or epsilon or everything, anything, right? but here we are representing it by this dash. This is not a blank, okay? This is not a space. This is a special character that we'll use for some special purpose, okay? Now what will happen here is that you see, this is the LSTM layer, so it has like 8 timestamp. So it will give us 8 characters, okay? Because it has 8 timestamps, so it will give 8 predictions to us, okay? And why I have 6 here? Because I have 6 characters in my vocabulary. So here I have one output, second output, third output, and so on. So I will have 8 different outputs because I have 8 timestamp, right? Now, out of these 8 outputs, I have to get this word. Okay, it may not have 8 characters, right? For example, Apple, it has 1, 2, 3, 4, only 5 characters. So how do I decode this raw output? For example, this is producing A, maybe blank, maybe P, something like that. And I have to convert this by applying a decoding into this word, which is Apple. Okay. So now let's see this carefully. This is the important slide, that how do we do it? I have 8 times step. So suppose this is the output. A, P, blank, blank means special character. Okay, P, L, blank, E, E. The first step that we do in decoding is remove the repeated symbols. Okay, so what is repeated? This E is repeated. Okay, nothing else is in a sequence. So I get this. Okay, so first step is remove the repeated you can say symbols. The second step is remove the blanks. So I remove this blank, I remove this blank, and I get Apple as an output, right? So this is the decoding. I have not told you encoding yet, right? So what is CTC decoding? You will have certain output from the LSTM. Okay. First, you have to remove all the characters which are repeating in a sequence. You will just keep one of them. This is the first step. In the second step, you will remove the special character, which we are calling blank here. And after this, you will get the output which we desire. Okay. Now, why we are doing this? Because now we see when you are training the model, how you will encode the text. Okay. Now, these are the 3 rules which I highlighted here, that you can encode a word using these 3 rules. So let me just explain them on the board. Okay. So the first rule is that you can insert as many blanks as you like at any position, right? For example, if I ask you there is a word go, encode it. Okay, so you can insert blank anywhere. This is one possible encoding. This is another encoding. This is another encoding. All of these are encoding. Okay, all of these, when you decode, they will give you go. How do you decode? Remove the repeating character. Step 1, remove the blank. Okay, sorry, this will not give you go. I have to be careful. Okay, so you see, if you repeat them, you will get back go. The second rule is you can repeat a character as many times as you like. Okay, so if we encode this word using this rule, what are possible encodings? This is go. Another possible encoding is maybe this. Another possible encoding is okay. When you decode it, what are the rules? Remove the repeating character and then remove the blank. There is no blank in this. Okay, I did not introduce it. So when you remove the repeating character, all of these will map to go. Okay, so let's go back and see these rules and then it will make sense. So we are saying we can insert many blanks at any positions as they will be removed in the decoding. We can repeat a character as many times as we like. And the third rule, which I did not tell you yet, is we must insert a blank between duplicate characters, which means that if we are encoding Apple, this P is repeating. So I must insert a blank between these 2 P's. Okay. Now, in order to understand it, let's see let's see one more example. Suppose I have to encode the word to. So what are the possible encodings? One possible encoding is maybe this. Okay. If you decode it, you get back this. Another possible encoding is maybe this. Another possible encoding is even this. If you decode it, you get back the same thing. Okay. Now see the word T002. Now O is repeating. I must insert a blank between these 2 O. And of course, I can repeat it as many times as I like. Okay. So this is one possible encoding. But if you say, I encode it like this, then this is wrong. Why this is wrong? Because when you decode it, you will remove the repeating character, you will remove the blank. So it will actually give you TO2 rather than TOO2. Okay, so the important point is that whenever you have a repeating character, you actually have to put a blank in between. Now let's put these pieces of information together, okay, and let's see how we'll practically be doing the decoding. Okay, so this is an important slide which will actually give you an idea. Now what is it? I have 5 timestamp, okay, and assume I only have 2 characters in my vocabulary, A and B, and I add the special character blank. So this is my complete vocabulary. Okay, I am trying to recognize this image. Okay, this is a picture of image of handwriting, and the transcription is actually AB. This is the ground truth transcription. Okay, in my LSTM, I have 5 timestamp. So for every timestamp, I will have a prediction. Okay, means I will have a probability for A, probability for B, probability for blank. Means I have a softmax layer with 3 neurons, and I have a probability for A at T0, T1, T2, T3, T4. Okay, so instead of writing numbers, the probability is color coded, that if it is like lighter, it is close to 1. If it is darker, it is close to 0. Okay, we are just using this convention here. Okay, so what we do, this important slide, so please, I would request your attention. At every timestamp, you can, one option is, rather the common option is that it makes sense that we pick the maximum probability. Okay, so at T0, out of these 3, A has the maximum probability. I pick A here. At T1, again I pick A, then I pick A again. At T3, this blank or special character has maximum probability, it is the brightest. And then at T4, I have B. So this is my output from the LSTM. Now I have to apply decoding on it. How do we decode? First step is remove the repeating character. A is repeating 3 times, so I just keep A. Then nothing else is repeating, so I get A blank B. What is the second step? Remove blanks. When I remove blanks, I get AB, okay, which was my actual transcription. So you see, when you are decoding, you just simply you follow those 2 steps. That first, pick the character with the maximum probability at each time step, then remove the repeating character, okay, and then remove the blanks. Okay, now one final thing for today, for which I'll be using maybe example of a slide. Let me go there. Yeah, maybe I explain it here. That you see, it looks very easy when we look at it from the perspective of decoding, but you must be thinking, how do I train it? Okay, because training such a system may not be easy, and for training, we use something in such type of system which is called CTC loss. So I'll just explain from this slide that how this works. Okay, how you actually compute loss in such a situation. So suppose I have an image, okay, and this is the image. Sorry, maybe I explain from here. Okay, so this is my image A. This is a picture. Okay, so I know that the ground truth transcription is A. Okay, this is the image, and this is the text, which is the ground truth transcription. Okay, and just because I'm doing calculation, so I have assumed only 2 timestamp, T0 and T1. Okay, and you have 2 alphabets A, B in the vocabulary, and a special character. Okay, now initially you initialize the weights randomly, you pass this image from the network, and it gives you these probabilities. Okay, means it is not trained yet, so you are getting some random number, 0.40, 0.6, 0.40, 0.6, and so on. Okay, now you have to compute the loss. So how will you compute the loss? Okay, this is important. This is your ground truth. Okay, and you have 2 timestamp. You have to see all possible ways of representing A using 2 timestamp. Okay, using the encoding which I told you. So for example, if I represent it as AA, this will map to A. So this is a valid representation of this A using 2 timestamp. What are other possible representation? Blank A. Okay, this will also, if you decode it, you will get A. Another one is A blank. Okay, so you see, I have computed all possible decoding, all possible representations of ground truth text A, which when I decode, I get back A. Okay, so since this was a very short sequence, so there are only three possible combination. Okay, if there are, you can imagine there are 3 or 4 timestamp, or even for a practical problem, maybe 15, 20 timestamp, that the number of combination would be large, right? But since we are doing by hand, so we have chosen a very simple example. Now, from this, you say, okay, what is the probability of the sequence AA? Probability of A at T0 is 0.4 and at T1 is 0.4. So the probability of AA is 0.4 into 0.4. What is the probability of blank A? 0.6 into 0.4. So this is 0.6 into 0.4. What is the probability of A blank? A is 0.4, blank is 0.6. Okay, so this will become, I think, 0.16 and then 0.24 and then 0.24. So these are the three ways you can get A. You can, since you can get A either through this or this or this, whenever you have or, probabilities are added. Okay, so you add them together, you will get, I think, 0.64, maybe you can verify. Okay, so you get this 0.64 as the probability of producing an A. But you see, what is the title of this slide? Loss. And we are computing probability, not loss. So what you do is you can take negative log of this, which can convert a probability into a loss. Okay, this is something common we do in machine learning. If you have a probability, you want to convert it into a loss, you just take the negative log. Okay, so this is the loss you are computing for this training example. Since it is not very easy, so I'll just give you a recap and then I'll stop for today. What we were discussing, CTC loss. Okay, CTC decoding, we already know how to decode. Just remove the symbol which is repeating as a first step, and in the second step you remove the blank and you have decoded. Okay, so it looks very simple from the viewpoint of decoding, but a tricky part is that how you will train this system. Okay, so when you have to train, we did this example that I have an image which is A, this is the transcription, and we assume that we have 2 timestamp. Okay, just because we are doing by hand. So if this is my ground truth, you have to see all possible ways in which I can encode A using 2 symbols. Okay, so one possible encoding was double A, because if you decode, you get back A. Another encoding is blank A, and a third encoding is A blank. For each of these, you compute the probability. Okay, what is the probability of A? 0.4 into 0.4. What is the probability of blank A? 0.6 into 0.4, and similarly for A blank. Since there are 3 possible ways in which you can get an A, so the total probability of getting an A, you add them. You get this number, which in this example is 0.64. So there's a 0.64 probability that you are getting an A. Now, since we are talking about loss, so a standard way to convert your loss, so sorry, to convert your probability into loss is to take the negative log. So whatever probability you are getting, you take negative log. So this is the loss for this training example, right? Similarly, you can feed multiple training example and then you can add the loss and you can back propagate and you can learn the bits, right? So with that, I'll stop for today, right? And if you have any final remarks, please let me know. Thank you.